Welcome to the thrilling conclusion of, we're on part 5. We're going to try and go from part 5 to the end here. Whew, that's a lot. I think we can do it though. Okay. Starting with, what is an ion? So an ion is a charged atom or molecule. Excuse me. Cation takes us a little bit more further. It is a positively charged ion. And then you guessed it, an anion is a negatively charged ion. Excuse me. All right, so C says, explain why a cation and an anion form an ionic compound. What does it look like? So when you have a cation, anion forming an ionic compound, what's happening is you get a transfer of electrons, right? So how this occurs is you might have sodium that has 1 valence, and then chlorine, which has 7 valence. Now, both of them want to achieve the octet rule. Sodium gladly donates 1 electron to chlorine, and chlorine wants to get to 8, so it gladly accepts. So the ions that form is sodium plus 1, and chlorine. Sorry, that one didn't quite fit. And chlorine minus 1. So this is your, this represents your cation. This represents your anion. Now these form a compound because they have opposite charges. So they're kind of like stuck together like magnets. You can almost think of like a positive and negative end of a magnet. They're stuck together. That's what a cation and anion are doing. What does it look like? These guys form crystal structures. Similar to what you saw in the potassium alum lab, where you looked at table salt, you looked at the alum that you made, it made these very patterned crystals. So that's usually how ionic compounds form. All of them have different crystal patterns just based on what charges are combining. And it says, based on the periodic table, what 2 elements form an ionic compound? Easy. It is a metal and a non-metal. These guys will form cation, anion. They'll be donating electrons, establishing opposite charges, and as I mentioned, getting stuck together. All right. Biggest thing with this is writing down formulas and or names given the opposite. So if we look at the first one, we have copper 2. So copper's plus 2. And then phosphate is a minus 3. It ends in an 8, which means you got to look it up on the back of the periodic table. You're going to find that it's PO4. Copper, of course, is Cu. All right, with ionic compounds, this is where you have to crisscross your charges. So the 2 is going to go here, the 3 is going to go there. You don't bring the plus or minus with just the number. So this is going to be Cu3, PO4. I can't change the PO4. That stays no matter what, but I need to show that I have 2 of them. The way that I do that is I put it in parentheses. So now my charges balance out to 0. It has a net charge of 0 because I have 3 coppers both at plus 2. 3 times plus 2 is positive 6. And then I have 2 phosphates. Both of them have a -3 charge. 2 times -3 is -6. So the charge is equal 0. That's how you can tell if you did it right. All right, aluminum hydroxide. Aluminum is Al, hydroxide is OH. Aluminum is +3, hydroxide is -1. You're going to crisscross, so the 3 goes to the hydroxide, the 1 goes to aluminum. It's Al parentheses OH3. You have to put the parentheses on hydroxide. If you don't, and you just put the 3 at the end of that hydrogen, it's actually going to be a different substance than hydroxide. So make sure to put parentheses around it. All right, let's go through these a little bit faster. Magnesium +2, oxide -2, Mg2O2, which you can reduce down to MgO. You're only going to reduce ionic structures. You don't need to reduce covalent, okay? Keep that in mind. Ammonium sulfate. Now, ammonium is +1, sulfate is -2. Ammonium is NH4, sulfate is SO4. The 2 goes to ammonium. It's supposed to be a 2 right there. And then the sulfite gets the 1, so we don't put anything there. Okay, lithium fluoride. Ooh, easy one. +1, -1, LiF. Don't even need to crisscross because it's equal. Lead 4 sulfide. So lead is +4 because the Roman numeral is 4. That tells you the positive charge. And then sulfide is really sulfur, which has a -2 charge. So you're looking at Pb2S4, which again you could simplify down to just PbS2. Mercury bicarbonate. All right, mercury is Hg bicarbonate. Oh, we're going to have to search this one out here. Bicarbonate. All right, HCO3 -1. Okay. HCO3. It's a +1, -1 charge because you got a Roman numeral 1. So I don't actually have to change anything. And that's it. All right, beryllium iodate. Beryllium is +2. Iodate, I believe, is -1, but let's look. Iodate. It's IO3 -1. So BeIO3. So beryllium, the 2 goes to the iodate. The 1 goes to beryllium, but we don't put the 1. So there you have it. All right. Gallium selenide. So selenium is -2. Gallium is +3. I feel like I probably should have a periodic table. Unfortunately, I don't have one in front of me. So let's just go to ptable.com. Yeah, gallium is in that aluminum column, so it is +3. Selenium is Se. The 3 goes to selenium. The 2 goes to gallium. So there you have it. Cobalt 3 nitride. So that's the charge, cobalt +3. And then nitride is really nitrogen, and it has a -3 charge. So it is just going to be, we can skip the reduction. It's just going to be CON because CO3 and 3 will just reduce down to CON. All right, we did it. Oh, almost. Barium dichromate. Okay, this is kind of an interesting one because you might look at this and say, oh, look, there's a di there. It means we have covalent. But this is like the one polyatomic anion that has a prefix. So don't get tricked by it. Notice the barium, it's a metal. Dichromate, I believe, is -2. Oh, let's look. Dichromate. Dichromate is Cr2O7 minus 2. Okay. So minus 2. So it's plus 2 minus 2. So we don't have to add any subscripts. BaCr2O7. Again, I don't really have to crisscross them because they're the same charge. You're going to end up canceling them out or simplifying them out anyways. So we just go with that. Rubidium's plus 1. Phosphide is minus 3. So it's RBP. The 3 goes to the rubidium. The 1 goes to the phosphide. So we just leave it. There you go. Titanium 3. Titanium plus 3. Oxalate. Oxalate is minus 2. I believe it's C2O4, but let's look. Oxalate. Oh, where's the ion? Ion formula. Go. Yes, C2O4 minus 2. All right, so titanium is TiC2O4. So the 2 goes to titanium. The 3 goes to oxalate. And there you have it. All right, ammonium's plus 1. Chlorate. Ooh, chlorate. Let's look. Chlorate. Chlorate is ClO3 minus 1. So we got a plus 1 minus 1. Ammonium's NH4. Chlorate is ClO3. Don't have to add anything. We leave it. Zirconium's plus 2. Bromide's minus 1. The 2 goes to bromine. The 1 goes to zirconium. So ZrBr2. Whew, we did it. All right, this is the flip. Now you got a name given the formula. And we got, oh man, another 15. Okay, we can do this. Rules for ionic naming. Let's look at the first one. You list the metal as is, lead. And then the non-metal, if it's a single element like oxygen, you just turn it to an "ide" suffix, so oxide. We don't really care about the subscript 2, although that does factor in for the name because we do have to include a Roman numeral for lead. So oxygen has a minus 2 charge. There's 2 of them, so the overall charge is negative 4. I only have 1 lead. That 1 lead has to have a positive 4. So it's really lead 4 oxide. Not every metal is going to need a Roman numeral. You got to check the back of your periodic table to make sure it's one of them. Okay, NH4 we know is ammonium. How do we know? It's on the back of the table. N is just nitrogen, so we call it nitride. K is potassium. S is sulfur, so it becomes sulfide. CO is cobalt. Now that's one that needs a charge or a Roman numeral. Cl is chloride. So let's look closer. Chloride is minus 1. There's 3 of them. Overall charge is negative 3, so cobalt has to have a plus 3 charge. So here we have cobalt 3 chloride. All right, Ba, barium. Cn is cyanide. And you know that from looking it up on the back of the table. Na is sodium. Br is bromine, but it becomes bromide. Ca is calcium. OH is hydroxide. Al is aluminum. S is sulfur, so it becomes sulfide. Sn is tin. Now tin's one that needs a Roman numeral. SO4 is sulfate. So SO4 has a -2 charge, which means the only thing that we have here is tin by itself. It has to have a +2. So this is tin 2 sulfate. Ag3PO4. Okay, so Ag is silver. PO4 phosphate. Silver does not need a Roman numeral. You can look it up on the back. It is in the cation chart, but there's no Roman numeral next to it. So we're good. All right, last 5. Pb is lead. CO3 is carbonate. But lead does need a Roman numeral, so let's look. Carbonate has a -2 charge. There's 2 of them, so the overall charge is -4. I only have 1 lead, so its charge has to be +4 to cancel out that -4. Lead 4 carbonate. Mg is magnesium. Iodine is I, but we call it iodide. Hg is mercury. And then ClO3 is chlorate. Right? Didn't we just look that one up? Yeah. And I'm pretty sure mercury needs a Roman numeral. So chlorate's a -1 charge. There's 2 of them, which means the overall negative charge is -2, which means the one mercury has to have a +2 charge. This is mercury 2 chlorate. Ba barium. N is nitrogen, so it becomes nitride. Ooh, and look at this one. That's a fun one. NH4 is ammonium. And then C2H3O2 is acetate. That's on your back. Both of those are in the back. Okay. I think we can do part 6 somewhat quick because there's not a whole lot of writing to do. All right. The intermolecular force, which leads to the strongest attraction between molecules. The strongest one out of these 3 is hydrogen bonding. And remember, this is when you have a hydrogen that is bonded to an N, hydrogen bonded to an O, hydrogen bonded to an F. If you have that within a molecule, it leads to intermolecular attraction or intermolecular forces between molecules. Okay? All right, so they're asking to identify the strongest intermolecular force present in each and then answer the question that applies. Bromine bonded to itself is nonpolar, so that ties to LDF. This is a hydrogen bond because it's going to experience hydrogen bonding between HF molecules. So that's going to be the strongest intermolecular force for HF. And then CH4 is London dispersion. So the highest viscosity is really asking for the strongest intermolecular force because it's going to take a lot to break apart those intermolecular attractions. And that strong intermolecular attraction leads to a more difficult flow, a slower flow. So that would be HF. HF should have the highest viscosity because of the hydrogen bond being the strongest IMF. Okay, here. The intermolecular force for this first one is going to be hydrogen bond. This one is nonpolar because it's just carbons and hydrogens. LDF. This one technically is going to have like a bent shape because of the lone pairs on this center oxygen. So you're going to see dipole-dipole here. Highest rate of evaporation. So that is also similar to the weakest IMF. Because if you evaporate fast, that means you don't have a strong force of attraction between molecules. It's easy to break away. So the weakest force of attraction is LDF. All right, 4 is a tricky one. 4, they're all nonpolar molecules. So they're all London dispersion forces. Highest boiling point is really asking which one has the strongest intermolecular force. But you might think, well, wait a minute, they're all the same. How do we know? You look for which one is the largest atoms, which ones are the heaviest. And if you look at the mass on fluorine, fluorine's 19, chlorine is 35.5, and then iodine is 126.9. Iodine's the biggest. So the biggest molecules, if they all have the same IMF, that's the one that's going to have the strongest, at least with London dispersion. Sorry, let's tie this just to London dispersion. If they're all LDF, you're looking for the largest molecule because that's going to have the strongest London dispersion forces. So you'd go CI4. And the reason why that is this one has the most electrons, not just valence, but core electrons within iodine. So there's more of a chance for those electrons all to congregate and create a stronger, very instantaneous partial positive, partial negative. It's going to be a stronger partial positive, partial negative compared to the other ones because they don't have as many electrons. All right, last two. This is going to be nonpolar. CO2 is nonpolar, so this is LDF. This is a bent shape, so it's going to be polar, but there's no hydrogen bonding, so that's dipole-dipole. This one's trigonal planar. Everything is the same bonded to the center, so it's LDF. Highest boiling point, again, is asking for the strongest intermolecular force. Dipole-dipole is stronger than LDF, so we would say SO2. All right, last one. All right, intermolecular force for diamond is we're just going to call it network. We'll say network covalent. Same with SiO2. NaCl is ionic. So which ones have the strongest IMF? It's going to be your network. They just have a stronger connection than the ionic structures do. It's too strong. Ionic is strong, but it's not quite as good as network covalent. Whew. All right, that's all of them. I hope this helps.